Alright, so we're ready to begin with hypothesis testing. So let's go through a brief introduction of what hypothesis testing really is. So firstly, what is a hypothesis? A hypothesis is a proposed explanation, it's an unproven one, for a phenomena. Examples of hypotheses are, if I eat less sugar, I will lose weight faster. Or if I drink more water, I'll feel more energized. Or if we use this advertising slogan, we'll increase sales. So as you can see, testing or proving a hypothesis is a very important field in statistics, and it's going to be immensely helpful in the business world. So how do we go about testing a hypothesis? Take this hypothesis. If we change the color of the Add to Cart button on our e-commerce website, we'll increase sales. To test this, we can foresee many problems though. What if the change was carried out when the end of the month was approaching? That is when sales are naturally going to increase. That's when people get paid, by the way. Or what if the company increased ads around at the same time, bringing more traffic to the site? What if there was some random event that resulted in a chance in more sales? As you can see, there are many difficulties in testing hypotheses. In reality, this is one of the most controversial uses of statistics, and doing a clean, proper hypothesis test is often quite difficult. So, how do we go about creating or framing our hypothesis? Firstly, we always start with a null hypothesis. This describes the existing conditions or the present state of affairs. That is, if nothing changed. So, a basic example is all lilies, that's a flower, have 3 petals. That's the existing conditions. The number of children in a household is unrelated to the amount of televisions owned. Or in a business case, changing the Add to Cart button color on our e-commerce website will have no effect on sales. These are all null hypotheses because they describe the present state of affairs or the pre-existing conditions. So we saw our null hypothesis. Now let's look at the alternative hypothesis. This is the hypothesis that's used to compare or contrast against the null hypothesis. So an example is, if we change the color of the Add to Cart button on our e-commerce website, we'll increase sales. And the null hypothesis in this scenario would be, users exposed to the new Add to Cart button did not change their tendency to make a purchase. Whereas the alternative hypothesis, in this case, will be phrased as, users exposed to the new button will result in increased sales. So that's how we basically frame hypothesis. Now you've basically got a basic introduction to this. So let's take a look at statistical significance and how it relates to hypothesis testing. So we're going to discuss a research design, what is called a blind experiment here, and it's often done by pharmaceutical companies in drug testing. So let's design an experiment to investigate whether a new flu medication reduces the length of time flu symptoms were experienced. So here's the setup. We need a group of persons, let's get about 80 volunteers. We separate the population into 2 equal groups of 40. So we have group 1 of 40 volunteers, which is called the control group, and these are given a placebo or fake pill. And now we have group 2, which is the treatment or experimental group, and these are given the real pill. Now the member in each group has no idea which pill he's getting, by the way. So let's move on. So now let's formalize our hypothesis. Subjects, this is the null hypothesis. Subjects taking the flu medication did not change the duration of the flu symptoms compared to those who took the placebo. That is, that the new flu medication had no effect. Subjects taking the new flu medication had the duration of their flu symptoms reduced compared to those who took the placebo, which is now our alternative hypothesis. So this means that the new flu medication reduced their flu symptom time. So it actually worked. So now let's go back to experiment. So in blind experiments, like I said, users are kept uninformed about the pill they're taking. So that way they avoid any changes in the user behavior. Example, those given a fake pill may attempt other remedies to their flu, which will affect our final results. Other caveats and issues with such a test is that assessing the participants on whether they really have the flu or not is some other type of cold is of concern. And then persons who know they're taking the pill may take less rest, assuming the pill will help, thus prolonging or worsening the symptoms. So if you're going, this means basically if you're going for like a medical test and they tell you this pill is supposed to reduce the flu symptoms, but you don't know if you got a placebo or not. You may want to assume and think positive, you got the real pill, and then you may perhaps go take on some more ambitious activities and probably prolong your flu. So let's talk about statistical significance. Once we obtain the results from the two groups, how do we interpret these results with any degree of certainty? Take a look at the results now. These are the actual results from our simulated flu test. Our control group had the average symptoms lasted 5.4 days. Our group 2, which is the experimental or treatment group, had flu symptoms for 4.8 days. So now you may see, oh, well, look, there's a difference. That means the flu medication worked. However, we can't conclude that. And that's why we need to look at statistical significance to be sure. So let's compare our means firstly. So the means, this is the means of the duration of the flu symptoms for each group. Remember, this is the control group, and this is the treatment group or experimental group. So our null hypothesis stated that there would be no difference between the means. That means the flu symptoms would last the exact same length of time. And our alternative hypothesis basically said x1 minus x2 should be greater than 0, which means that the ones who weren't taking the flu medication should be bigger, should be longer, okay? So in fact, our alternative hypothesis seems to have checked out, because 5.4 is greater than 4.8. But should our null hypothesis be rejected? Now let's ask ourselves a question. Would this happen every time? So here's a thought experiment, okay? Control 1, our control group, had flu symptoms of 5.4 days, and now our experimental group had symptoms of 4.8 days. Now ask yourself something. If we were to repeat this experiment in future at another time, would the means be exactly the same? And because our sample size is relatively small at 40 persons each, meaning things can change in future. We don't know. It's quite likely every time we repeat the experiment, we'll get different values for these means. So imagine if we run this experiment on our placebo control group several times, and each time we got a new mean. So this was our first mean. Now imagine we did it in future. We get this, we get this, and we get this. You don't know. It can actually happen because every time we run an experiment, because of random variation, our means are going to be somewhat different. So now we have to do something called a permutation test. So each time we redo this experiment, it's called a permutation test. We do this so that we can calculate the distribution of the test statistic for each trial or iteration of this experiment. And we call this distribution the sampling distribution. So now let's talk about the sampling distribution. Our sampling distribution approximates a full range of possible test statistics for our null hypothesis. We then compare our control group mean, which is 5.4, to see how likely it is to observe this mean. We do this by rerunning our control group test several times and observe whether a mean of 5.4 is likely or rare. So just to give you a gist of what we're proposing here, is that we want to run our null hypothesis, our control group test again and again to create a distribution of results. So we take means that we will get there, and we basically plot them in a distribution, okay? However, in the real world, we can't rerun our control group studies several times due to time and money and effort and constraints. It's just not practical. However, we don't need to, and here's a trick. Okay, I'll just go back to this diagram here, just to illustrate the control group and the experimental group, what they look like. So recall our results. These are the tables of results here for 80 people, and this is the group they belong to. This is just a simulation of the results here, and their flu duration symptoms. So we now take some of the individual data points and randomly assign them to the other group. We then calculate the new mean after this randomization. So remember that I showed you this is a simulation of our control in our experiment. Let's see what we do. So take a look at that. What we just did is that we took some individual data points and randomly assigned them to the other group, just like this. So why did we do that? And after we do the swap, we then calculate the new mean after this randomization. So let's take a look at how it looks. So imagine we're moving subject 1 in our results table from control to experiment, and we're doing it randomly for some users in this group, and the total remains 40 each. Okay. So for each iteration or trial, we log the mean and the mean difference. The mean difference is our initial mean 5.4, which is our control mean, minus the mean of the randomized trial reassignments. So take a look at how we do it here, okay? So we have simulation number 1, and we get the mean of the control group after doing a swap, and then we get the mean difference. And we run this simulation maybe up to 10,000 times. So we use these means to now create a sample distribution. So let's just pause here because I don't want to lose you. So what we did, we have our results. Let's go back to our results here, okay? So, and then what we've done, we have now randomly assigned or swapped the groups each user is in. And then from that, we get the mean difference. And we basically use this mean difference now to calculate our sample distribution. So that's it for here. And now I'm going to bring you to hypothesis testing p-value, where we look at how we actually validate whether we should hold on to a null hypothesis or not. So I'm sure you guys are excited about whether we should drop our null hypothesis and accept our alternative hypothesis from our last lesson. And now to do that, we need to look at something called the p-value. But before we get into the p-value, let's run those simulations we talked about in the previous lesson in Python. Okay, so go to your Google Colab notebooks and open up this one, Statistics 5 Hypothesis Testing. I already have it open here. So what we're going to do, we have some simulated results for our drug trial here. So let's load this data set. Okay, so there we go. So now let's just take a look and see if our groups are control and experiment as we expect. Yes. So now let's show the means of our control group and our experimental groups. So to do that, we just basically get the control group here by doing this df group equal control and get the mean, and likewise for the experimental group, and we print the results below. We get 5.4 and 4.8 as we expected. Now, this is some little code I created. What it does here is that it swaps the groups randomly. And it runs 10,000 iterations of this simulation. So first we get the mean difference. We just create a list from our mean duration of data points. That mean duration is what we have in this column here. Basically, it's how long the flu lasted for each person. And then we'll store our mean differences in a list, and this is the number of iterations we specified. And in this loop, goes to 10,000 times. We create 2 empty lists for group 1 and group 2. And for each data point in data points, that's this length here, this list here, sorry, we basically we randomly assign it using a random int, either 1 or 2, I believe, or 0 or 1. And we basically, if it's true or if it's false, because I think 0 or 1, 0 would be false, 1 would be true. And then if the random assignment is true, we append the data point to group 1, and if not, we append it to group 2. So that's how we basically randomly go through all our list, all our simulations here, and then randomly swap the groups. And what we do here, for each time we swap after this is finished, we get the mean difference using NP mean of group 2 minus group 1. That stores the mean differences here. And we basically append the mean differences into our mean differences list. So let's run this. Should take a little while because it's 10,000 iterations. So let's wait patiently. There we go, it's faster than expected. And look at what we have here. We've generated this plot of mean differences. So the mean differences, remember correctly, are after we do a swap, it's the mean difference from group 2 to group 1. So remember how we had 5.4 and 4.8? So 5.4 minus 4.8 is the mean difference for that first initial experiment. And now we're doing this for 10,000 simulations of those results. So this is interesting. So now how many values exceed, this should be D, not a T, the mean difference of 0.6. You can see 0.6 was the mean difference we got last initial trial. And that doesn't come up that often. It's actually kind of rare. It's at the tail end of this normal distribution curve. So let's take a look at this here. So we just convert this mean differences list into a pandas array. And we basically just use this to check and see how many differences in this 10,000 simulations exceeded that 0.6. And we get 381. So that's not much out of 10,000. So now let's go back to a PowerPoint and we'll discuss how we calculate p-value. So this was our results from our Python simulation, and the mean differences mean, that's this point here, was actually close to 0. So this plot shows our normal distribution sample of mean differences, and remember our initial mean was 0.6 here. So let's take a look at this. How do we use this now? So what can we take away from this? We can see that in real life, our mean difference of 0.6 lies a bit far to the right. We see that the mean in our experimental iterations is almost 0. This means that the mean difference between the groups is almost purely random, and there is no real difference between the groups. But how do we show this statistically? What is the probability of the mean difference of 0.6 occurring? So let's check our mean difference values and see how many of these values were greater than or equal to 0.6, sorry. So now this brings us to p-value. The probability of exceeding our original mean difference, 0.6, is known as our p-value. So quite simply, our p-value is the probability that this 0.6 occurred given our results. So if our p-value is less than our predefined threshold, then we can reject the null hypothesis. This means that a difference in means between the control group and experimental group was statistically significant. Okay? So read this line again. If our p-value is less than a predefined threshold, then we can reject the null hypothesis. In our example, this would mean that our medication works. So a common p-value threshold is usually 5% or 0.05. So let's determine our p-value in Python. Now before we go to our Python notebook, because it's just one cell of code that we need to run, I can intuitively tell you our p-value was 0.0381 or 3.81%. And how did we get that? Remember, in our 10,000 simulations, how many results exceeded 0.6 in our mean differences? Only 381 out of 10,000. And that's how we get this figure here. It's 381 over 10,000. So remember, our p-value threshold was 5%. So this is definitely below our p-value threshold. And as such, our new flu medication does in fact appear to work. So a p-value threshold of 0.5 means there's a 5% chance that the results can be attributed to random coincidence. This means that our difference in means, that is 5.4 minus 4.6, was in fact statistically significant. So let's talk a bit more about p-values. So we've shown that our results support the alternative hypothesis, and that is our new flu medication reduces the length of the flu. However, always remember p-values are the probability that what you just measured is the result of some random fluke. So saying our p-value is 3.81% means our results have a 3.81% chance of being attributed to random coincidence. However, 3.81 is small, and it's typically lower than the 5% threshold used for p-values, and therefore we can say our results from our experiment are statistically significant. And like I promised, this is just a basic code. We need to work out a p-value in Python. So if you go back to your notebook, Statistics 5 Hypothesis Testing, you can quickly see that all we just did was take how many times our mean differences here exceeded 0.6. That was 0.6 in this chart here. So remember, we got 381. Let's just run this again to confirm that. All we do now is just put 381 over the number of iterations, which is 10,000, and that's how we get 3.81% or 0.0381. So at this point, you've completed hypothesis testing using the p-value. That's the basics of hypothesis testing, and later on in much further lessons, we'll do another round of hypothesis testing with A/B testing, which gets a little bit more technical, but it still basically follows the same principles we taught in the last hypothesis testing with p-value section. So for now, we're going to look at hypothesis testing using the Pearson correlation. And what is Pearson correlation, or do you remember what correlation even is? So Pearson's correlation coefficient, R, tells us about the strength of the linear relationship between x and y points on a regression plot. Now that might seem very vague and a bit mathematical to you. However, it's actually quite simple. So what exactly do we mean by a linear relationship and a regression plot? So let's take a look at this. This is a very simple chart here. We have different subjects here. These are people. These are the ages, and this is the annual income. So what we want to see now is basically, does age relate to annual income? So what we're trying to say is, do older people make more money than younger people? So this is a plot here, all right? This is annual income on the y-axis and age on the x-axis here. And you can see the points scattered across this plot here. So what is the Pearson correlation coefficient? Well, we're going to come to that now. So hypothesis testing with Pearson tells us whether we can conclude two variables correlate or influence each other in a way that is statistically significant. So R, as you can see here, ranges from -1 to +1. Values close to 0 indicate no correlation. Negative values indicate an inverse relationship and strong correlation. Positive values equal a positive relationship and strong correlation as well. So you can see in this plot here, as one value increases, the other value increases. That's a positive correlation. Here there's no relationship between values being large or small, affecting these values here. And likewise, this one, as values get larger, these get more negative. So there's a negative correlation here. So R measures the strength and direction of a linear relationship between two variables on a scatter plot. So you may be wondering, how do we determine R? And this here is the actual formula for calculating R. So now let's go through a step-by-step process on how we calculate our Pearson correlation coefficient. So we know our null hypothesis, we stated no correlation between income and age. That's basic. Next, we define alpha. Alpha is a new term we're introducing here. It is our measure of significant strength, so lower is stronger in this case. So we'll use 0.05, similar to how we use our p-value threshold at 0.05. Next, we find our degrees of freedom. So our sample had 10 subjects. That's rather small anyway. And the formula for finding degrees of freedom is df is equal degrees of freedom n minus 2. So it's 8 in our case. Next, we use an R table, and we'll take a look at the R table on our next slide to find something that we call the critical value of R. That is the threshold value we use to reject our null hypothesis. So in our case, using an alpha of 0.05, we plug alpha into our R table, and we get our critical R to be 0.632 from our R tables. So if the R we calculate using this formula is greater than our critical R, we reject our null hypothesis. So we apply the formula now. So this is the R table I mentioned. So this is our degrees of freedom here. So we're on 8, and we know our alpha, this is our alpha value up here, is 0.05. So we get 0.632. That's how we use that value right here, our critical R. So now we have to calculate our R from this formula to see if our value is greater or less than our critical R. So remember, if R is greater, that is, if this R is greater than our critical R, we can reject the null hypothesis. So let's take a look at this. So remember, let's go back to the big formula slide. Take a little while. This one here, these are the values we're going to calculate now in our table. So let's go back to our table quickly. There we go. So we have X, which is the age, Y is the income, and we square the values here, and we have the product here. So now we can just plug these things in to this formula here. And basically we summarize all of this, what we just got, into this, and we get 0.482. So does 0.482 exceed our critical R? No, it does not, unfortunately. So therefore, in this case, we need to now accept null hypothesis that given our data set, there is no correlation between, or at least no statistically significant correlation between age and income. So you've just completed the Pearson correlation coefficient hypothesis test to see if two variables influence each other. How would they influence each other if it's statistically significant? That's what the test tells us, and you've just worked it out. So that's it for this lesson. We can now move on to machine learning.
Subscribe now and press the bell icon. Never miss an update.